welcome. So this is kind of year 3, what we've done here, and it's working with Matt and ISU and the electrical program, and kind of it's a different aspect, right? It shows you another part of the electrical world. It's not just about string and wire and stuff like that. There are motors, and and that's the main way that they get a product, whether it be water or a slurry or a powder, from point A to point B, is either electricity or fuel. So those are the two options. So it's a pretty safe industry. There's lots to learn for sure on it. But like I said, my name's Gabe Gibbons. I've not done the electrical side. I'm not an electrician, but I am a motor guy. I've done it since 1997. So like I said, it's a good industry, and hopefully what you guys will get out of this is just a little knowledge of what you're looking at when you look at a motor, things that when you're testing it with your meters and stuff, what you're actually testing. So anyway, hopefully you guys have lots of questions and we can answer them. So I'll turn it over to Justin.
All right. I'm Justin Farr. I've worked for S&G for 8 years now. I got a start in construction electrical. I went through the apprenticeship, and I am a licensed journeyman electrician, and made the transition into the motor aspect of it all, like I said, about 8 years ago, and it's one of the best things I've ever done, in my opinion. I still get to mingle with the wireman side of it all, out in the service side. It was actually it was shell shock for me, going from what I did to what I do now. Mostly for the fact that in the program, there really isn't, you learn motors, but only to a certain depth. And so it was really nice to actually understand and really it can be intimidating when you're out there, be it maintenance, be it anything else, out in the field, when you really don't deal with it that much. And so it's been a good experience, and I actually really love what I do. It's something that a lot of people don't get a chance to do in their life, and so I'm very fortunate for that. So
my name is Matt Neeser. If you don't know who I am, we probably need to talk because you haven't been paying attention for the last few months. So anyway, I started my electrical back in 1998. Sorry, Gabe, I don't mean to age you. That's fine. So I've been doing it for 24 years. I've been through construction, maintenance, did my own business for a while, and motors is a passion for me. I love it. I mean, I love working on the heavy industrial stuff, the stuff that'll kill you right now, not later. But there's so much with these motors. We were talking before, and understanding when you're troubleshooting certain readings that you have to go even deeper. And these guys are awesome. They've done this for the last 3 years, I think. Fourth year. So I work with them weekly. So 3,600 and something
in one plant.
Yeah.
So that gives you a pretty good explanation.
And like say now, about 2 years ago, I took over the role as the reliability engineer. And so we work really close, like, fine tuning things. I'll send them motors that aren't broke yet, that we're going to refurbish. We're going to steam clean, whatever. And then, in fact, we got one coming up here next week. But even down to the bigger motors, we traveled to Corpus Christi for our big 4,500 horse. So yeah, like I said, these guys have go into more of the mechanics. We're doing this week's class, it starts to break down the pieces of the motor. So getting to see that and see how they're balanced and the rotor bars and how different things function will be very beneficial to you guys, so that you can kind of get past that point. Hopefully when we get out to Simplot, those that can come, we'll get more into the controls portion. But anyway,
cool. All right. Yeah. So I think what a good place to start would be, like Justin, he said he's our service guy, right? So they go out and check these motors in the field. So obviously the things that you are going to check for, I guess, I mean, your main thing is a meg reading. Megger is your reference to ground, right? I mean, you got to have an infinity, or at least not a 0 on your meg reading when you're checking reference to ground. So Justin, if you want to grab your tester, I don't know, this one's a Fluke. I'm sure there's many different models that they make, but
We'll try to make test. You done one? Well, so he's right. What we have right here is a Fluke 1507. I've used Fluke for a long time in the maintenance side, and so far this is the best insulation tester I've come across. Relatively cheaper compared to others. Right now I'm using the double clamp. They actually have a remote mode on here with it's just a external probe where if you're doing heat trace, for example, with a known resistance, you can actually probe it and find what part is bad along those lines. So I just like how flexible this unit is to use. So right here we got a little 60 horse GE, and what we're doing is, first thing you do when you walk up to it, even be it in the field or even here in the shop, you're going to want to look and see, check for, play Captain Obvious for a little bit. Do I see smoke? Do I see excessive oil leaking into the windings? And that can kind of tell you a lot. So next thing you know, you do is you check the nameplate. This is a 460 volt motor, and so at 60 horse, you're around 73 amps, which should, where you should be. That's another thing, if you do get it to test run, about what you're looking for clamp on ammeter. But for right now, we just want to make sure that if we start this thing up, it's not going to blow up in our face. So hook a ground side up, and right now it's freshly painted, so a little difficult to find it, but we got one right there. And our internal windings on how we do our windings is a lap wind. So basically everything in here is interconnected somehow. So I can actually just clip onto one of these leads and it'll read through everything on it. So 460 volts. So we're going to go up to 500 volts on our tester and just hit test, and you'll see it's maxed my megger out. So that would be the equivalent of an infinity reading on it. We can check this by hooking to the other leads real quick and read through. We're reading straight through coils right there. So technically, there are no blown coils at that point. So that's a good sign. That's what we want to look for in the field, or even here in the shop. And this is actually kind of the first step in our disassemble and our troubleshooting process here as well. So
quick. So when he pushes this test, you're going to see a voltage down at the bottom. If you're testing on 1,000, it's like 1,096 volts. So if you have something that's leaking, that voltage will come up and then it starts to creep down. So that's an indicator of you got leakage on there.
which moisture,
Moisture's good.
grease. If your winding's really dirty, you could have a lot of leakage, not necessarily be dead ground, right? But a leakage, which would mean that it probably needs service. It's on its way to failing. So
Yep.
so,
I got a question on that real quick.
got a question.
yes.
So what's the difference between doing that test and a continuity test?
Okay.
What's the difference between doing that test and a continuity test?
Okay, so that's actually a really good question because we get a lot of those here.
Yep.
We've run where the customer says, "Well, I rung it through and it reads straight through." That's great, but to ground, in reference to ground, a continuity test only will go through the coils phase to phase.
That's right.
Megger test stresses the windings in reference to ground. So you're actually putting a almost nameplate voltage in DC current through the motor to stress that insulation and make sure that we're not going to ground instead. So you could actually use a continuity test in a possibility of a short,
Possible, yes.
or a blunt, or an open.
And what you're looking for would be a disparity, right? Between the two. If you had a blown coil,
Yeah.
two of them would be
go
close.
together.
One would be way off. Right?
Yeah.
Okay.
I
Like
mean,
I said, I'm not the electrical society. Just make sure.
the other part of
Yeah.
it, continuity doesn't induce the voltage, so you may not get a solid reading.
Yeah.
You might flip it.
What do you got?
I've had a situation where I've done a continuity test on a motor
Uh-huh.
and then done a Megger test, and the Megger punches straight. Like I didn't get anything on the continuity, and the Megger just punches straight through.
So,
Yeah, continuity.
and I in all the years I've done this, I tell people I don't put a whole lot into a continuity test on a motor. I really
I'll
don't.
do continuity coil to coil.
Yeah. But you can have two identical motors that have different readings. 200 horsepower.
Yeah.
That's what I'm saying. So,
So actual resistance usually doesn't matter. It's just the coil resistance. But
but what you're looking for would be a big disparity doing it that way.
So putting it into kind of perspective, where a continuity test would be a good test, would actually be in the control side of it. Let's say you have a motor fail to start, and let's say we're dealing with a square D, right, on a size 5 starter. When you ring that out with an ohm meter or a continuity tester, the resistance on a size 5 square D coil should be around 27 ohms. If you get any change other than that, because you can have two coils that look the exact same right next to each other. One's 27 ohms, one's 12 ohms. Which one's going to start? 27 ohms. Because that's where your continuity tester would be very, very helpful in the field. With just a lot more along the lines of the control side versus the actual motor
In
side.
isolation, right?
In isolation.
You're isolating which leg you've lost or
Exactly.
which leg is low.
Yes.
So,
So we've got the motor measured. We know it's not going to go to, or it's not going to ground. We got a rough view that it's not going. That we don't have a shorted coil because it read through all 3 legs. So we can actually hook this on up and test run it right now. We got oil in that, right?
yes, sir.
Okay, we got our level. So this is a vertical hollow shaft motor, and
Good point. Yeah.
that's one thing you want to always make sure of. Do not run these without oil. Never run them without oil. So,
So, for instance, this motor is coupled to a pump that either it could sit as a depot on the ground or a short couple pump, but the shaft is connected to the pump down low. Shaft runs up and comes through this. This is a clutch or a coupling that ties the shaft to the pump. So when you're turning, as it comes up, it brings your water up and pumps it out. So
all right. So on a test pad, we really don't want to hit 460 volts to this straight on because this isn't hooked to anything. So this is set here and
it might try to jump.
it'll try to take off. So what we do is we step it on up. We start with around 60 volts AC, and then we'll slowly ramp it up.
Like
Kind
a
of
soft start, if you will.
Yep.
Stepping up the voltage.
electrically shifting gears. Exactly. So we're gonna pull out our e-stop right there. Here we go. Everybody ready?
Yep.
Want me to go in the right direction? Good.
Normally this would be turning counterclockwise, but
Yes.
it's not hooked to anything, so we're okay.
Okay. There's 120 volts.
30 volts.
Here it goes. It's going to torque it a touch, but not much.
Okay. Grab your ammeter.
Check your amps right here. We've got 39 amps, 37 amps, 40 amps.
Okay. So 37, 39, 40 on the amperage. Which nameplate? It was at 70 something,
Yeah,
but that's normal because it's not loaded up. Okay. But what we're looking for is the evenness. Right. You're going to have a little bit of vary, and I'm sure Matt would attest to that. Depending on what our incoming voltage is going to affect our amperage. Okay, so if you have a higher leg, obviously the higher voltage leg, your amperage is going to be lower on that leg. So, but that's pretty close. Yep, connection. Yep.
Resistance in the wire.
Yeah.
The resistance in the wire can cause a little bit of a variable.
That's
you
true.
know, so,
Yep.
you know, starter, all that stuff, depending on where you're actually taking the reading.
When you're winding up one of these motors, is there like a certain protocol, because each of these windings is going to have a certain amount of inductance?
Yes, that's
It's
right.
going to affect the motor.
That's right.
So is there a certain, like, you follow instructions for how to wind it up, or do you have like an equation that you use to
So there, yes and no. You are right. So you have to have a certain inductance in the motor to make it. Because this would be called a squirrel cage motor, ultimately, and the rotor chases the magnetic field, right? So if you don't have your pitch for that coil set right
In the right spot.
in the right spot, you're going to lose torque, horsepower, and speed.
Yep. So in a roundabout way, there's a lot of mathematics
A lot of mathematics.
that goes into involved, because you can have 200 horsepower, 1800 RPM motors, and they can have different data.
Yes.
Okay.
We have right now we have 750 horsepower motors, and out of the 4 have the same amperages or amperage ratings, and the rest are completely different.
You
But-
mentioned pitch.
Pitch,
How
yes.
does that? So I
Well,
might have learned this, and I just
No.
forgot.
no, we're going to
fine.
get into that actually.
Yeah, we'll
Answer
get into
you.
that here. in
Yep,
just a
when we
little
show
bit.
you a winding, we'll talk about the pitch and how that affects.
So real quick, when you're out troubleshooting, and say you got a high amp situation, right? So one of the things that you can do is just like what Justin just did and ran this motor unloaded. So when you look at that nameplate 70, whatever it is, we're about 40 amps. So you should be at like, I think it's 45% of nameplate.
Yeah, that's pretty close.
So I
Yep.
think it's about 45% of nameplate. If your motor runs at 45% of nameplate, problems on the mechanical side.
Yep.
Okay. So it's a kind of an easy. You worked at Lamb Weston, so you understand dealing with mechanics. Everything is always electrical.
Don't miss it.
Yeah.
I do all the time. Prove them wrong. But yeah, that's a good way to check it. You know, if it's a simple uncouple or whatever, you can go right to that test and say uncouple it. The motor's running as it should.
So here's I'll just throw this in there real quick. It was an example of a situation I ran into. We did a motor for a guy. He came and picked it up, and it ran fine on the test bench, tested fine. Came, picked it up, called me 2 hours later. He says, this thing won't run. And he said, it runs fine with no load on it, but as soon as we load it up, it won't run. So, and that was at another motor shop. We didn't do field work, but my boss says, go out there and see what he's got. So as I'm pulling up to the application, it was on a crusher for a construction company. As I pull it up, he comes walking out. He's like, oh, just drive around. As I'm driving over, I'm running right over the SO cord that goes right to that motor. And I was not the first one. And I was by far not the smallest vehicle that ran it over. So we got to looking, and sure enough, with no load, there was even though those wires were broke, that's what the problem ended up being. There was enough there to run it until it was stressed. if that makes sense. The cord was crushed. Once there was load on it, there was not enough service because the stranding was broke to run the motor. So it was, exceeding because it was low voltage to your motor. And so anyway, something else you can run it. The motor was fine, but it was in the wiring going from bucket or controls to the motor.
Which brings us into service burial code. I mean, right there.
Had it on the road.
Yep, just on the road.
Yeah. So
Yeah,
Yeah.
you see that. You actually see that a lot.
yeah.
A lot, and especially in the maintenance side of it all, you'll walk on up and into the control side, and you'll see where it's something that people move around a lot or jumps a lot, and you'll see the strands starting to break around a little spade connector, and it's holding on by two strands. Of course.
And
you're
what
gonna
does
have
that do?
problems.
That builds heat,
It's heat.
and heat's gonna take out your connection, or and could possibly even go all the way into the winding.
Is cramp. You put that crimp on there. Like these are crimped pretty solid. They've obviously used the NEMA-rated crimp.
Yep.
Joe. But if somebody takes a pair of vice grips, right, and hammers down on that, they're not getting the proper connection. So when the connection's different, you're creating those heat points, which is where your wire breaks, and then all of a sudden it cascades out to a breaker problem.
Yes.
Because that's the coming from your feeder to your motor, you're depending on those lugs and connection to be tight to carry all the current to run the motor. So okay.
Any questions so far?
Yeah. No?
Nope.
So I'm trying to think where else stuff that they might encounter like out in the field at this point.
So here's a question. Let's say you get called out to a motor, and you do just what we did. We measured it, and it's a low mega reading. Okay, but it's not to ground. Let's say it's 1.5 meg. What you've been in this situation? What would you do?
Well, I'd go grab a vapor tester. So I'm cheap.
Yeah. No, that's true. I mean, we have that option.
Yeah. And then we'd know, so this is a really basic read, right? Sorry, you're not getting that. So our guys out at the plant, they have a magnet. They come up and they read it. They call me, and I've had motors that come back at like 1.8, 1.9. Before we had the instruments that we have with the PDMA or the Baker, the dynamic tester, any of those things, you almost had to go with your gut. Like, yeah, it's got water or something's not right, which is, but really with those instruments, then you're able to break down a lot more of what's going on. Because there's so much in a motor. It could be a broken rotor bar, could be a nick, or like on our TG, we had a stem that broke off on it. It's a DC. Well, when that thing would spin up, it would come into contact, but when it would wind down, it would disconnect. And we actually went through all these tests and came back as clean. Well, a guy stuck a mirror in there and seen the cracked solder in there. So we ended up doing a full rewind. So some of it's luck, some of it's journeyman instinct. You guys ain't there yet.
Here's another one. We'll actually show you that motor. There's one of 4 motors, and it's in our shop right now, and we'll glance at it later. But it came in here for a recondition. We tore it apart, steam and baked it in the ovens. We're baking all the moisture out, tested it, and tested great. So talking with the customer, having the good relationship with the customer, he's like, well, it's intermittent when it's either, failing and not starting or starting. So come to find out, the application where that motor runs, when it's running, it's like 400 degrees. Okay. So what we did is put that stator back in our oven, and we heated it up to, it wasn't quite 400. I think it's around 300 externally, but still your motor's getting, hot. We heated it up to 220, pulled it out and tested it, and they failed. Okay. So what the heat did is it just expands it, and it actually was grounding out because of the heat. But you have to put it in its running state or get it close to it to see why is it failing. And it was heat related, and they do run hot. You know, that one runs because of the environment that it's in runs hotter than normal. But even this motor out in the field will run hot when it's been running for a while.
So I actually know where this motor comes out of. Yes, nameplate is 70. I believe it's 72 amps on this, and they actually run this to around 84 because the pump's a little bit bigger than this. So it runs it into what's called the service factor. This one has basically 1.15 service factor rating. So you take your nameplate current times 1.15, and you can technically run this motor to that. It's not good for it, and it's not really the best thing to do. But in this case, where it's outdoors, exposed to direct air circulation, and I mean, they have a pivot going right over top of it too, so it's not really having an overheating issue. And they've done it for years. They've done it for years, right up till the point of failure. So
and what that does, it just decreases the life of the motor, right? I mean, heat's a killer, so obviously the more amps you're drawing, the more heat you're building. So it's just decreasing the life of the motor. You know, but
So a 10-degree rise on the external of the motor will cut the life in half. Yep. So for every 10 degrees, you can just.
and another thing that goes along with the running and the service factor is elevation. Right now we're close to a mile around this elevation. So this 60 horse is actually not a 60 horse. It's probably more like a 57 horsepower because of the elevation. So, yep. Derating factor. And all motors are nameplated at sea level. So, anyways, yeah, that's not a real common point, but I just thought I would throw that in there because that elevation does have a lot to do with it. You know, the thinner the air, the less the motor can cool. So,
That's good, and that's like important that we kind of touch on the nameplate stuff.
yeah.
the other thing I've ran into talking about cooling is everybody runs everything off drives now. We can control the RPM, we can control the current, we can control all of that. One issue I've ran into multiple times is it's a certain frame motor and a 900 RPM in that frame just kicked the bucket. And we need this thing up and running by the end of the day. So we throw an 1800 RPM motor, same frame and everything on it, and we dial it back on that drive to 900 RPMs. Well, what's going to happen? Are we getting the airflow from that 1800 RPM fan?
No, it's rated.
No. You actually have to pull that fan off that 900 RPM motor, throw it on the 1800 RPM, or else it's going to burn up.
And a lot of times you might even have to put an air hole in it.
Yeah,
You might have to.
exactly. So there's little things like that you know, I would have never thought of that when I first experienced it. But you run into it, and once you kind of think about it, you're like, oh, okay, that makes sense. Now, what you got?
So I run into a lot of motors that are run at various speeds.
Uh-huh.
You know, you might run it at 20, 40, 50% speed, depending on the purpose.
Yes.
That motor might be rated 1800 FPM, but we never swapped out the fans on those motors.
So if it's
Is it like
inverter
an-
rated, it changes things.
Yeah.
So you got there's a insulation class on there. So typically your standard is F.
Yes. That class now.
So H is typically inverter rated, so that gives you a higher range of temperature. So our 4500 horse, when we sent it down to Corpus Christi, we actually upgraded the insulation to the H class. Even though we're not running a VFD on it, it's off a soft start, we still have higher temperatures on that motor as standard. We used to put a water cooler in front of it, which causes a whole bunch of other problems.
Yeah.
You get into corrosion and all that kind of crap. So the insulation class kind of determines what.
On the winding wire itself is where that's
And
different. The wires probably got more coats of varnish on it, and the insulation around the coils is probably thicker or something. You know, so to help with the heating of that. So
And that, like, so when he's talking out on farm, you don't have that insulation glass
Yeah.
out there.
Yeah.
They're, they're, you know,
If it turns and it runs and it goes,
Yeah.
that's all. That's all that matters. You know, it's yeah.
On the way.
Yeah.
well, they even have farm duty rated, and they're pretty low class motors.
Yeah.
I mean, they'd never survive in
no,
Are they the most common insulation classes? F and H.
Say it one more time.
Are those the most common insulation
yeah.
classes?
Nowadays, yeah.
Now with the specs that motor manufacturers are required to follow, at least in the States, they have to meet a certain efficiency ratings to even sell. So outside of our country, I don't know the rules, but
So, for example, over here we got a car wash. I went out to a service call too. The motor was grounded for one of their pump systems. Cool. It was put in 20 years ago. Never had one problem with it. We'll just order a new motor. We put in an order for a new frame and everything. It gets here, it won't fit. Because they changed the efficiency rating, they changed the insulation rating, they changed everything on that style of motor per the government regulations,
which changed the frame.
which changed the size. So it was half an inch too long. Wouldn't fit. So we had to actually have that motor rebuilt.
We've had the same thing our life, so we're
Yeah.
not even that old.
Yeah.
I mean, it's mattered like 10 years.
Yeah.
And it's a couple inches, but when you get into these industrial facilities, a couple inches is a big deal.
You can't just pick up a tank and move it.
Right.
So-
Exactly.
Yeah, we just had one in here. I'm pretty sure they built the plant around it.
Yes.
It was pre-1942.
Yeah.
It was pre-NEMA. NEMA is like a standard that the electric motor world went to in 1942. So all of your 60 horsepowers followed this frame size. You know, this is a vertical. The horizontal motors are what they consider a T-frame motor, and that framework is the mounting bolts on the base and the shaft size, shaft height, all that goes into your frame size. So most of them should follow that nowadays. There is still those OEM exceptions, but
That's one thing you got to be careful with. OEM exceptions. So they'll bring in, and hydraulic pumps are very well known for this. So they'll bring in like a 56C motor, but then they manufacture it, whether they change the shaft and put a spindle on it or whatever, and put it on their equipment. So if you go and order you a new 56C, it won't match up.
yeah, 56 comes with a 5/8 shaft, but there's no say, you know, the manufacturer might have built a 56 frame with a 7/8 shaft. So you could run into different stuff like that, which makes it OEM. So,
You know, we run into this with tunnel fans a lot actually too. So
What does OEM stand for?
I actually don't know what OEM stands for other than,
it's original equipment manufacturer.
there you go,
Okay.
right? It's like a specialized, it has its own specs
Okay.
that it's built to, right? So it makes it hard for the people to just go in and buy one off the shelf.
Yeah, okay.
Yeah.
So whether it be a motor or a contactor or whatever, you know.
So yeah, our tunnel fans, for example, the ones I've been talking about, came in there at 445 TCZ frame. So that's a T frame motor within the footprint, C face, a Z is for specialty shaft.
Yep.
And usually with a tunnel fan, it's a shorter shaft
Shorter shaft or double shaft.
or a double
A lot
shaft.
of times they'll have shafts on both sides. You
Yes.
stand on both sides.
And so that's kind of what he's getting into is there's so many little things here and there that when someone calls up and says, well, I have, like I said, a 56T frame, you're sitting there like, okay, but can you bring it in and show it to us so
Yeah.
we can get some measurements?
Well, and some things can be manipulated around. So if you have like a 324 TS, that's usually a short shaft.
yes.
But if it's on a pulley system, you can put a standard T in there as long as you've got the root.
Root, yeah.
And that's what you should put in.
Yeah.
You know, typically the S's, correct me if I'm wrong, but usually go to pumps.
Yep, and they're high speed.
Yes.
Right, 3600. So,
Yep.
you know, a motor, it actually doesn't like, bearings don't like to run 3600 actually. So, Yeah, the life expectancy of a 3600 RPM bearing would be at half, I'm guessing, of an 1800. And when we refer to that, motors typically follow certain, because of the mathematics, follow certain speeds, right? So 3600 is your fastest, 1800, 1200, 900, and so on and so forth and down. And there again, Justin said earlier, the smaller or the lower the speed, the bigger the motor is, because it needs more casting to cool. If that makes sense, because it's moving less air, so it needs more of the iron to help dissipate the heat on the motor. So
Plus, they are courses.
yep, they are.
Ones that are moving the heavy loads.
So I think if you don't have questions here, we could probably move to this section over here, and we're gonna touch on the different parts of an electric motor. So once we've ran a motor and determined that it was good, it spun, and everything was fine, we would then go ahead and finish disassembling it. Those two things, those are the stator part. That's the part that has the electrical coils in it, or the copper coils in it. This would be the rest of the parts. This is your rotor, the rotating apparatus. And then you have an end bell on each side, or a bearing, or a end bracket. Some people call them, or end bell.
Okay.
And that's what these are. And these contain your bearings, which are on your shaft. So that's your support for the rotating device of the motor. So then once you apply your power to it, like I said, it just starts running around, and the rotor is always chasing it, trying to catch it.
These are your bearings.
Yep. This is just a shielded ball bearing.
So basically, that just moves around like that.
Yep. And that actually sits right here. Here's the bearing fit. So when we're measuring the motor or checking it, reconditioning it, we check the bearing fits on the shaft, the bearing fits in the brackets, and make sure that those they have to be, what is it? I can't remember the exact specs on it, but yeah, tolerance is
Here for
plus.
for a C3 fit, which is what we use mostly, it's plus or minus 4 thousandths
That's on the bearing, but that's not on the fit.
on the bearing. Yeah, not on
That's
the fit.
on the bearings itself. Yeah, I can't remember what are exactly. I'm not a machinist, but
Yeah.
anyway, they'll measure them if they need sleeved or fixed on the rotor. Then we can do that. So like I said, this is a form coil. We just barely got done rewinding this one. This is a random wound motor. We make these coils in-house. This is like copper bar or form coil. We actually have to order these. And there's probably a dozen manufacturers in the United States of the form coil version. All of your high voltage or higher voltage, 2300 and up, that's actually considered medium voltage, right? But in the electric motor world, I call it high voltage, but because most of our stuff is 480, so yeah, the form coil that's all you'll ever see on a 2300 volt and higher, is the form coil, because the random wind doesn't hold up to the higher stresses of the voltage, the higher voltage. Lead wire is another one. You can see that this is a 200
That's 200.
200 horsepower. This is a 400 horsepower. This is 4,000 volt, pretty small lead cable, only 3 leads. This, because your voltage is lower, your current is higher. So this needs 6 leads paralleled to carry the current capacity for that 480 volt motor.
So real quick, does everybody know why this has such a high amp rating? So this has, what size is this?
It's probably six.
Number
But
6.
with
So if I ask you what was the amp rating on number 6, you pull out your cookbook, right? So this has a significantly higher rating than what THH and XHHW has. Notice the strains.
Yep. Oh, I see what you're saying. Good point. Yep. It's different than feeder wire.
It's different than standard THHN
Okay.
or XHHW. So this is, plus it's flexible. Okay. We use this in tons of places. I have rolls and rolls of this stuff in my plant. So we use it in a lot of places, especially on buckets coming from the bus bar over. A lot of the older stuff is brittle. It's 2HHN and all that kind of stuff. So we'll swap it out with this, and I don't know what 2-aught goes up to like 260 amps or something.
Probably we have a chart back there too.
Yeah, on your 600 volt wire. Yeah.
Just like you guys would follow, you know, we have the same type of standards. We have certain lead wire for certain ratings. So
Now it is more expensive too.
So now,
it is.
what would give this wire a higher rating than that wire there? You guys think?
Voltage or current?
For voltage, what would give that such a higher voltage rating than that? There you go.
Yeah.
That has about double the insulation
Right here.
that your standard
The black part.
number 6 has
Yep.
in the field.
Yep.
And so,
What were you saying about the standard versus?
So if you look at the number of strands,
yeah.
Okay.
there's significantly more here than your standard THHN.
Okay.
Right?
It's
Because
probably
it's
like
the
90,
copper. a little
Yeah,
bit
so
more.
THHN from, I believe, from number 6 up, they stick with 27 strands of copper, and you'll notice in like
Per conductor.
yeah, per conductor.
conductor,
And
yeah.
so for like your anywhere from a 250 kc mill up to a 1,000 kc mill, they've even gotten their compact, where I don't know if you've seen them, where they'll do a polygonal center conductor, and then they stack it with 27 strands
on the outside.
outside to make it a compact conductor.
What was that question?
So he asked if there's a different table to refer to. So this, I don't know if this is in the code or not.
It's
I don't know.
think
In
I
your
think
electrical
there's some
book, I'm not
reference
sure.
Stuff there.
We have a book,
Yeah,
right?
you
That
guys
tells
have
us.
to have it, but-
there's
Yeah.
a reference in the I believe in the table section back in the back, but it doesn't come out directly and talk about it. It actually, I believe it leaves it in the hands of the authority having jurisdiction to make the call on them. So,
A lot of them aren't going to understand what you're doing with it. So you usually have to bring out the table and say, see, right here. But yeah, it's more used in motor manufacturing type stuff. But like I said, you know, if you need the flexibility in certain things, like on your buckets, that's where we use it.
well, I'm glad he brought that up. Has anybody done any installs in buckets at all?
Probably not yet. Oh,
Okay, you have? Okay, what's the biggest cable size you ran in a bucket? Okay, so
What was the answer?
Eight.
about an 8.
Pretty small. Like, yeah, smaller than that.
Yeah, so
The feeders to the bucket are usually a little bigger, but I
Yeah.
haven't
Yes.
seen those are done.
Prior
Those
to.
are, I've never had to rerun the X's.
okay.
Not yet.
So a couple situations I've been in, Matt's been in it too, where they give you about a 2 foot by 2 foot bucket. Your breaker's in the top of that, and you have about 3 inches to bring 3 500 kc mills in the top of that breaker. Now, I don't know if anybody's bent or tried to bend 500.
With that tighter radius,
Yeah, with that type of radius,
and had it
It's-
survive.
it sucks. It sucks bad. And so that's why he's saying when you get a product like this,
Yep.
it'll easier to come in, and actually will have a higher ampacity rating than your standard 500 kc mill. You go with it every time.
The other thing too is on your THHN, when you crank that over, you create that stress point.
That's right.
This stuff doesn't stress that
That's right.
because of the multiple.
It's because it's pliable.
Yeah, you have,
A kink is a path of least resistance. There's a resistance there. It's going to create heat if you have a kink wire.
and you,
Plus it's a violation.
yeah, you have band radius you have to follow. So, yep.
Okay. Oh, just to kind of let you know, there was a twin to this motor we just sent out last week that rewound. It was also a 400 horsepower, but it had less coils than this one. So it kind of goes back to where you were talking earlier with the mathematics involved, right? Our last one was a 72 slot motor. This is the same speed, but it's 90 slots. So being an 1800 RPM, you do poles times phase, right? 4-pole motor times 3 phase equals 12 groups. So there's 12 groups of coils in here, and you can probably see them. Here's a group, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So where it's 90 slots, we've got alternating groups of
7 and 8.
7 and 8, yeah. So there's like a group of 7 and a group of 8, group of 7, group of 8.
72 slot with standard 6 per group.
12 groups of 6 straight across the board. Most of them are the higher horsepowers are. That's a 72 slot motor. So it's got 12 groups of 6 in it. Most of them are 72 or 60 slot.
72, 60. Sometimes
Some
when you get
48
yeah, 48
on the smaller one.
Some submersible motors they get into with some odd ones where 54 slot. There's some of those.
Yeah, but that's
not
not for this class anyway.
Yeah.
So, but it gives you an idea of what you're looking at, you know, as far as what your leads tie into, what the inside of the motor looks like. You know, so like I said, it's just a giant magnet.
I got a
don't know where
question.
the rotor is to this motor. I think it's actually right there on top of that stack right there. But like I said, depending on, and when we get a motor in here, we cut it to burn it in the burnout oven in the back, which we run for what, 10 hours?
We do 10 to 12 hours.
10 to 12 hours on a burn cycle at 800 degrees. Because what we're trying to do is burn all this varnish that is encased this winding. We got to burn that off and get that copper loose so we can pull it out of the slot and count how many wires we have in each slot. And that tells us, you know, what to go back with. So some might have one wire in hand and 30 turns, and another one might have 10 wires in hand at 5 turns. It just depends. That's why we got to cut it and burn it in our oven and pull it out and diagnose it.
So far, the biggest one we've had that I've been part of is 34 in hand. Or no. Yeah, 34 in hand.
I think it was.
And 6 turns of 34.
34 individual wires. Our hopper only holds 20, so we had to fab some stuff to make it work. But a lot of copper involved. Yeah, I think that one. It was, how big was that motor? 600?
600.
Yeah, it had almost 700 pounds of copper in it.
And each group of 6 in that case weighed about 60 pounds.
Yeah, so
Just
depends, but that's part of the process is when we burn it out in the burnout oven, and we have to pull it and count it and take all the measurements so we know what to go back with. On one good, yes sir. Sorry, that's your hand. Yes, exactly. Yep.
Could you repeat the question?
He asked, does each group represent a phase, right? And the answer to that is yes. So if you would say, you know, phase 1 or A, phase 2 or B, phase 3 or C, and then A, B, C, A, B, C, A, B, C. So, yep.
And then you get into a little further, kind of what you were talking. We get into poles on this. So this would be considered a 4-pole motor.
Yep.
So basically, all the A's at a certain time will energize in 4 places. All the B's in 4 places. All the C's in 4 places. So that's how you get your 1800
Trying
RPM,
to catch it.
and then that rotates electrically as it goes 60 times per second in the United States. So that's how you're getting your speed, is your poles in your motor. So
Yep. For instance, like a 3600 RPM has 6 coils. It has half of these coils. So it's got ABC, ABC. So 2 poles, right? Your poles are directly across from each other. So
If there's less load,
Yes.
yes,
However, so here's a good.
he said less poles makes it faster, and the answer to that is yes.
Yes. So here's a question for you. What's the difference between, let's say, this motor here and a synchronous motor? Anybody here? Okay,
synchronous motor only runs on the
you're exactly right. These motors,
What was it? Well, why was it?
a synchronous motor always runs at the same speed. So and they put out the same torque output and everything. Synchronous motors lock up. So it starts as a squirrel cage motor at first. They get it rotating, then they hit a DC synchronizer, and you'll actually see the rotor cog and lock up and synchronize. And if it doesn't synchronize in most places about anywhere between 2 to 4 seconds, then it shuts the whole system down. But these ones have what's called slip. So on this motor here, it's an 1800 RPM motor, but nameplate 1780.
Yep.
So that difference is your slip, because the rotor's chasing that field, but it never catches it once it's loaded. So
you'll see some 1800 RPM motor, but it might be nameplated at 1785. It might be nameplated at 1755. You know, it just depends. So,
and you're going to see more slip the higher the speed you go.
Yeah.
So 3600 RPMs are usually around 3490.
Yep.
3540. 3540.
Yeah.
Yes.
The higher the RPM, the less torque.
Yeah.
Right. So, yeah, if you need some with a lot of torque, you usually decrease your speed to get more torque.
Yep.
93 probably most common is going to be the 1200 and 1800 and the 36.
Yep.
1800 is kind of your, I call it an engineer's best friend. They just pick an 1800 and they'll do most of what they need it to do.
Yep. Yeah, because of 3600, like I said earlier, and you can ask bearing manufacturers and they'll tell you that I think it's around 2900 RPM is actually what bearings are designed to not exceed. So the fact that they're running faster than that, their life expectancy is just dropping. So,
and it takes more copper to wind at 3600 RPM.
that's true. Your coils are heavier.
Yes.
Yep. You'll have less slots, less groups, but more wire.
Well, the other thing about the 1800 is you can do a lot more with it. 3600, there's pretty much almost no reason to put a VFD.
That's right.
Right? Yeah. Because once you get down on a 3600, once you get down to about 50%, it hates it, and the amps start to climb, and you don't run. So an 1800, you can run it down to like 20%, and they don't care.
Yeah.
So
You get a lot of excess vibration too.
Yeah.
The lower you go, when you start noticing drive or a motor doesn't like it, you can start rattling like crazy.
So when we get back over to the winding section, I'll kind of cover the importance of the insulation value, you know, kind of what we were testing earlier. We were doing a MEG test. So what we're testing is to make sure that the coil is insulated from the laminations, which is the steel. Obviously, if your insulation ever breaks down, and as soon as your copper wire touches your frame, that's going to create a blow spot or go to ground. So it's very important. You know, all this white stuff, that's what that is, insulation. These actually come in one coil at a time. We put one coil at a time on this one. And then you can see all these are commons. Okay, we tie all those together with solder, insulate, so all those are protected. This, a mush wound, so we would actually, if this is groups of 6, our machine would make 6 coils at once. We'd pull it off and lay that group in and spin up another set of coils. Like I said, so 6 at once, 6 in a group on that one. These are all done individually and then tied together via solder afterwards to make that a whole group. So if that makes sense. So
This one's
Yeah.
a lot more time consuming, but a better end product.
This one?
Yeah.
Yeah. And there's more evenness to them too, and we can see it on our tester when we test the form coil versus a random wound. Yeah, just because they're all identical, but these are all formed to the exact same shape. Yeah, like you said, end bells, bearings, rotor, those are all things that we test and measure to make sure that the fits are all good. And if not, then we machine them to spec. So I think we can probably, if we just want to turn around, we've got a DC here. We can kind of just go over that real quick. Like I said, the DC motors aren't quite as prevalent as AC motors, but they definitely have their place. The cool thing about DC is it's constant torque at any speed. So if this thing's running at 3 RPM, it has the same torque as if it's running at 2200 RPM. So that's the cool thing about DC is, same strength, even if you slow your speed down, whereas in AC, you slow your speed, you're slowing your torque. Yeah, DCs are built strong. A lot of them in the ski industry, on the chairlifts. These actually go to the haul trucks. You've seen the big haul trucks, like on mining, they have the big, huge tires and all that. Each one of these haul trucks has a couple of these grid blowers on there, don't they? Yeah. And all these do are to try to keep everything else cool, because there's a lot of heat, right? And I've never seen them in place. I just know, what they go on.
It blows dust and debris off of the cooling system.
Yep, tries to keep everything cool. So,
Yes.
yeah.
So now in here you see the two different size coils in there. We have a field coil right there.
Yep.
We got an interpole coil right there. So why would we have to have an interpole coil in that? In the original first DCs that came out, you would really only have 4 of these big coils here. Why do you think they threw the interpoles in? Well, you're partially right. It's basically for efficiency.
Yep, to realign everything.
Yeah, so this coil here is going to be a north.
A north. Yep.
That one's going to be a south. Well, your flux is going to try to go north to south, right? Well, it doesn't do this nice perfect arc like all the theory books tell us. It actually comes straight out and almost jumps straight across. So it's skewed. What an interpole does, so if this is a north, that one's going to be a north, and it helps push the flux into that curve, giving you still your constant torque as well as a more efficient rotation. So what are the 3 types of DCs in the field? There's actually 3 different types of winds. Series is 1. This is a series wind. Shunt or compound. Yeah, that's 2. And parallel. So this is a series, and it's all in how it's wound. It just goes in one side and out the other. That's series. Parallel uses, you have to energize everything individually. And then you have a shunt or a compound, which actually is a combination of both. So
a DC, the armature or rotor, rotating device, in this aspect, it's called an armature. They are wound with coils also.
yes.
Whereas a squirrel cage or an AC motor like that one, it's just either form cast aluminum, poured cast aluminum with end rings on it, or sometimes they're copper bars. On the heavier dutier stuff, they all come with copper bars through the rotor. But on these, most motors nowadays are produced with the die cast aluminum poured, versus where these actually have, the windings in the armature, the rotor itself.
So here's a question for you. Let's say you're out there, like we're over at Simplot, and you've been running a motor, no problem, for a while. There, Matt, and all of a sudden you start picking up a vibration that's not mechanical. What could the cause be, do you think?
Could be the bearings.
Okay, so you change bearings, still got a vibration. Now let's say it's only around 54 hertz on a drive. Good. Yep, mounting. So let's say you eliminate that. What's next? You still got them. There you go. So in these rotor bars, you see right here, they're poured individually. Or not individually, it's all one big pour, but like he said, it's poured aluminum. And we ran into situations where, yeah, around 52, 54, 56 hertz, that motor will almost start rattling right off the base. And it's because they had a porous rotor bar. So yeah, so it wasn't fully broken, but it wasn't fully connected either. And so you wouldn't know that until you got it.
I'll be honest, you don't see a whole lot of rotor bar problems.
No,
I mean, I can count probably on two hands in the 20 plus years I've done this that it came in with broken rotor bars.
Yeah.
So it's, you know, normally there's other failure points before the rotor bars.
You're right.
Especially with, you know, unbalanced voltage and stuff like that. You know, that'll do a number on the windings for sure. And the thing about a winding electric motor is it's like a book. It usually will tell you why it burned. You usually can tell the diagnosis of what happened, depending on the way it burned and what pattern it burned with and what. So, yeah, so on the armature, we've got, I mean, there's insulation below the windings, so it doesn't come in contact with the ring on the armature. Like I said, you can see we've got it all wrapped. This is one we wound before it came back for recondition, but that was a good one, I thought, to show that was, we wound that one. So replace the this is the commutator. Your brushes will come in contact with your commutator, and that just helps with
basically your brushes make a contact for your power to this.
Yeah.
And this will help
energize.
To energize this. So your field here is going to energize to a certain voltage and current, and then you're going to be able to control rotation right here through those brushes by inducing a magnetic field, by increasing your current. You know, in your if we're talking about in like a truck or with the haul trucks or anything, that would be your drive motors, or they're going to be hooked to the accelerator. So every time you do that, it's it's a literal rheostat that you push on. It increases voltage and current and everything, and it turns those big tires. And so proper terms would be the traction motors, what they are. So basically the haul trucks are like a locomotive, because that's what they use. Same thing, same technology. It's a generator on wheels. So
yes, sir.
I have read that BC motor you need a starter port. So like I've read that with certain like designs with DC motor, if you start them, it's a 50-50 chance it goes right or left. So they use like a starter coil to make sure that it always goes
Directional.
in the same direction.
yeah,
That's right.
I don't see one on this one.
no. That has been shifted in what's called the neutral ring, which is on your brush holder. So you can actually
Which
take
is right here. That's what these two leads go to right here.
Yeah.
Is your brush holder.
yeah.
It's disassembled, but it would sit in this bracket right here, and the ring itself would mount. The brushes would make contact. Like there's two there, two there, two there, two there.
Yes. And so in this case, what would happen is, because we don't have that, you shift neutral a little bit to one side, and it likes to turn that way. That's where you get your lower amperage. That's where it just runs smoother. If you reverse rotation by swapping polarity on your leads, you'll notice it's noisier, it's higher current, it just doesn't run right. And so you're right. It's some do that. A lot of them, like your larger ones, use equalizer coils to help with that. So your equalizer coils help with the start instead of having to actually put a set different set of coils in with it.
Which your equalizer coils actually would lay in here below your coils here.
Yes.
So it all helps balance out in your commutator.
Good
If
question.
I can get my zip drive, may have to have you come to class one night. I've got a zip drive. We have a turning gear generator at our plant that was just rewound in November. So I've got a video of all those coils coming out, so you can actually see how they lay.
Yep.
And you can see all the diodes and everything. So
Because your
Give me that, I'll post it.
your equalizer coil pitch or span is going to be way different than these.
Yeah.
At least the couple we've wound, they were significantly different. They were almost wound, ran 180 across from each other. Pretty close.
And you know, talking about generators, you know, we don't actually do the generator windings here, just because that's kind of a different animal. You know, you're talking about like rotation. In generators in the field, we've all ran across it where you lose excitation. And we have excitation coils or this excitation system in there where you either have a self-excited system or a onboard excitation system, which would be a battery, 12-volt battery. I've been in an instance where I've been dealing with a 480-volt generator and I'm getting 14 volts out of it. Well, somebody, when they were hooking up the leads, knocked the connector off of the exciter, and that caused everything. Yeah, you had to make. Yeah. Exactly. The self-excited, that's what you find in the rotor is they'll have a diode pack on the front, and that basically changes your voltage to help make up that leg.
like I said. So ours is significantly bigger than
Yeah. Yeah.
I mean, it's a 17 megawatt generator.
Oh yeah.
It's a big one.
It's baby.
Yeah. But you can see all that. I've got pictures. I've got a video of them actually unwinding, and it's kind of unique because these coils are like this, and so they take them out piece by piece. And there's like 27 stacks of copper bar, and they actually don't rebuild the copper. They send it off, have it cleaned and rehardened because it'll
Which
form.
is amazing.
Yeah, it's quite a
cool.
process.
Yeah.
Like I said, first time I ever really encountered it was in November, so now I'm not even close to next week, but I know more.
Yep. It's cool to see them, right? It's
Yeah,
cool to
it's
see them
great.
when they come apart like that. So
And like I say, anytime I'm doing stuff, like the reason I have a relationship with these guys is I've taken ownership of everything of their motors. So if I have a motor coming up here, I want to know what the hell went wrong with it. So I've come up here, they've cut bearings for me. You know, I've been here when they open it up because, like I say, you can learn a ton just off that first part. You know, our readings will tell so much. I'll be like, hey, I know I've got a ground in this motor, but I want to see what kind of ground.
Yep. Where it was, was it burned edge of slot? Was it burned in slot?
Turn.
Yep.
Or like the ones, we ran like 3 of them up here, and it was basically burned up by the operator. So too many starts.
Too many starts,
And I mean,
right? Because they don't
I've
have.
got pictures of those. Paul out and he's sharing with the class. So. But like it was bam, bam. I think we had 2 up here within 24 hours.
Yep. And they blew the exact same way, like identical.
Almost the exact same place.
Yep. And it was in the center. It was in the center of the slot, right? Which is your hottest part. I mean, especially a lot of start and stop. That's the hardest part on a motor is starting up. So when you have 6-7 starts in an hour, you know, it doesn't it just if it was only that bad. But see, that's a lot of starts. So it starts, runs up, and either trips out or gets turned off or whatever, and you start it up again. Well, it never was able to cool from the original start, right? Because it's about 10 times on startup. You're what they call inrush. Okay, so if a motor pulls 100 amps on that startup, that initial cross the line start, it could be 1,000 amps. You know, so if that did that, and it built up all that heat, and it didn't have any runtime to help cool that motor, then that's what caused them to burn, was too many starts in a too short a time.
Yeah, and if you look at like that 400 horse there, so you can start that, it's like 1.25 times in an hour.
Yep.
So how do you start at 0.25 times an hour? So you have one start, and if it don't start, it needs to sit and cool for like 20, 30 minutes.
Yep.
And then you can start it again. I mean, obviously that's taken over an average, but
and that's
4,500 horse, I've got limitations on it, and they start it. Unfortunately, the way the process is set up, it has to start like 6 times on the start up. So it's spanned over a certain amount of time. And obviously not enough cooling, but it's also a little bit different.
Yeah, that's because you've regulated it, right? You guys know. I mean, that's the most important motor in your whole plant, right? So they're one of them for sure. And
I've got about 350
that are most important,
depending on the day.
That one's at least the biggest for sure. So the hardest to change out, I would guess. So,
they don't just
anyway.
pick one of those off the shelf.
No.
That's the thing.
No, if they lost that motor, it would be probably over a year to have a new one built. So
that one's a custom. So
yeah, maybe even longer. That's right. Yeah, in several $100,000. Several $100,000.
Well, and to kind of put it into perspective for you, that standard frame is about 12,000 pounds for that size of motor. Our motor weighs 26,000 pounds.
Double.
So it's double. Yeah, over double. So what happened is, because of the way that it has to operate, we overbuilt the coils. So we actually purchased it from the motor manufacturer, sent it to another motor manufacturer, who re-engineered it, oversized it, and this is the one that goes to Texas. So oversized it, basically changed the cooling. It's got some internal cooling plus external cooling.
Yep. So
It's impressive.
now we can kind of look at this one. I figured this one would be a good one to show you. This is one that just came in for a recondition, and it had a bearing failure because this runs a pump, and don't know why. I didn't see it running, but it obviously was spraying water up through the shaft and into the motor, which actually took that bearing out. You can see how it's all black, and it actually galled to the shaft. So that's what happens when you replace oil with water. It's not a good lubricant. So steel on steel with water, it's just bound to fail. So, but at least the windings still check good. So, you know, what we'll do in this application is steam and bake the stator. It looks pretty good, like it's got a pretty good coat of varnish on it. So we'll just clean it up and test it. If it tests good, then, you know, we'll just put it back together. Sometimes, if they've been out in service for a long time, we've got a varnish. We'll dip and bake, just re-insulate that with varnish. We'll submerge it in there, heat it up, submerge it in there, and then bake it to cure it again. Our rewind process is a little different varnish. It's called the VPI process, which is vacuum pressure impregnation. So it takes, like on a form coil, we do 2 hours per cycle. So we'll drop it in the tank, pull a vacuum on it, which at this elevation it gets down to about minus 22. Which what that does is pull all your air out. Then you apply the varnish from our storage tank into the dip tank, and then apply 90 psi for a couple more hours. So it draws all the air out with the vacuum, and then once your varnish is there, it's pressurized back in, and it really makes them bulletproof. They come out and that copper is no longer pliable. It's like it's in concrete. So, but if it's just a recondition, we don't run it through that varnish. That's only on a rewind. So we've got our the older varnish for a dip and bake purpose. Typically 5-6 years, right? Is that what the rotation is for? for the motors that you guys do out in the field?
Yeah, we do a 5-year rotation for the most part. There's some that they push the envelope a little bit, 7 years. So far, with that rotation, the 5-year rotation, we've basically cut back from having 4 or 5 rewinds per season to maybe we'll have 1 rewind every 3rd season.
So just by, for instance, the customer he's talking about, I think they have 180 something motors.
Yeah, 174 just in this area.
Yeah. So they go through and check them, and you know that would be kind of what you guys would be doing. You know, they check the panels, you know, blow all the dust out, clean them up, get all the mice. If there's mice in there, because inevitably they find their way in everywhere.
Lots
panels,
of mice.
motors, they always everything. But that's what Justin and another guy do, and they go through and service those 170 motors every year. And then, like I said, we pull about 20 to 30 every year, right? With that rotation, it's every 5 years. And then by doing that, you know, like he said, they lose 1, maybe 2 every couple of years versus I know people that have many less motors than that and lose more than that in a year because they're not on a rotation where they're being babysat every year. So
well, and the thing about it is now if they have more motors than normal blow or go to ground or have issues, even with the pumps, it's usually of the acts of God status. Lightning strikes, so a pivot gets stuck and it's literally dumping water into these things. I mean, or the seal on the top end of the pump blows out and it's shooting water right into the windings. Then you just have the general human aspect where, I mean, you hear stories of they tried to listen to a bearing with a screwdriver and it goes into the windings type stuff.
We have pretty big, like 45 horsepower motors for AMUs in Glen Weston for the new section of the plant.
Yeah.
Wired wrong by the installers. I think my boss looked at it and he was like, I think what we've got is like, you know, instead of, it was somehow both in parallel and in series at the same time. He was amazed. He was like, how did this even run for like 2 months?
Yeah, there's different hookups for different voltages for the motors. So if you have a dual voltage motor, usually it's a Y start delta run, right?
not
a Y start delta run, but basically you'll hook lower voltage, all of them across the line, and then at higher voltage you have to use some jumpers.
That's on the 2300/4160 connection. Usually if you have 6 leads, you'll have on the higher voltage you'll have 3 start together with 3 going to line. If it's 230 you would have them parallel.
Yeah.
So on 230/460 volt motors, most of them come with 9 leads. So just depend on what voltage you needed. You know, and all the motor manufacturers come with a nameplate or at least a wire schematic usually in the J box or on the side of the motor to help you wire for whatever voltage you need.
Yes.
And if you have a 12 lead, you have to do
Or if it's 12 lead, yeah. Some manufacturers, which you know,
don't like 12 leads.
yeah. I mean, in all honesty, and you guys will learn this as you go on, especially if you deal with motors, 3 leads is very friendly, right? The only thing you're going to do with 3 leads is spin it the wrong direction. You're not going to blow it up because you can't hook it to the wrong voltage. So as long as you're the right voltage, it's got 3 leads. Like when we rewind them, in most cases, our customers ask for just 3 leads back. So there's no messing up with the 6 leads or 9 leads. It's pretty explanatory with 3. It's either, and then like I said, it's either going to spin the right way or the wrong way, and all you got to do is switch 2 lines to get your directions to switch. So, yep, 3 leads is pretty safe. So usually when we rewind it, a lot of times on the bigger horsepower, you have to run parallel. You just don't have big enough lead cable to carry the current for that. So we'll do 6 leads. But Matt can attest to this. I'm sure he appreciates 3 leads at any time we can do it. And then if we do go 6, at least proper labeling. So,
Yes.
right?
Yeah.
So, which we do a good job here. In fact, if we ever do 6 leads, we put metal tags on them and then put clear shrink tubing over the numbers to hold them on the lead, so they can't ever break or fall off. So
I think 45 will give us.
does it?
Yes.
But they're probably pretty big.
Yeah, they're big.
Yeah.
And then you got parallel feeds coming along. So
Yep.
well, actually, that's our design determination point.
Yep. So I don't think really anything else on this part. You got the balance machine right here. I want to just spin that up real quick and kind of show you. That's like I said, that's part of the repair on an electric motor is anything that's in rotation that's going to affect your balance. So we've got a dynamic balance machine to rerun and check all this stuff with. This is the die-cast poured aluminum barred rotors. So each one of these lines is a bar, and then this is an end ring, and that's an end ring. So all that's held together, and that's what that's what makes the magnet. This is always chasing the stator windings. So these fins serve a couple purposes. One is cooling, and 2 would be for your weight, for balance. So you can see this one has some weight here before. So seeing a bunch of weight right here, okay, that makes me feel like that there's some weak spots or voids in some of this poured aluminum right through here. I've seen them in classes where they cut them open and it actually was almost completely void in some of the rotor bars, but yet still tested good. So, I mean, it's obviously weak, and if you had a super fast tester when that motor's running, because what's going to happen when you have weak spots on your rotor is it's going to climb, right? So you'll see your amps would climb, but it happens so fast that our equipment can't pick that up. But like I said, it's a motor or a rotor can have weak bars and still work.
So we're trying to understand how he's talking about poured bar. So I don't know about all manufacturers, but Toshiba will actually inject it from the bottom. So you have this mounted like this, right?
Yep.
And they're injecting
Aluminum. Yep.
through the bottom, which helps eliminate some of those voids. But if you think about how fast aluminum cools and melts, you'll still get bubbles. And
Yep.
things like that.
Yep.
So
Yeah, and that's kind of what, when you see a lot of weight on a rotor in one spot, it could just not mean that the rotor's bad, but it could just mean that, the pour had some weak spots or voids, if you will, air bubbles. So anyway, this is a vertical. When we balance it with all of the gear on. So like the top bearing hub, the clutch assembly, that's the part that ties to your pump shaft. We balance all of that together because that's all part of the rotating device. But for this one, just for the class purposes, I wanted to just throw this, just the rotor in there and show you. So I've already kind of calibrated it and ran it, but it's just like a tire. I mean, a dynamic balance tire. You're going to spin it up. So this motor turns at 1800 RPM. But we don't spin this at 1800 RPM. We spin it, usually we go around 3 to 350 RPM, but we tell the computer what speed it's actually going. So it sets the parameters. Obviously, the higher the speed, the lower or more in balance you have to be, right? Your specs lower on the faster the speed. So anyway, spec for an 1800, I think, is 1.2 mils of vibration, which I don't want to bore you with all that, but obviously at 3600, those numbers are lower. So anyway, I'm going to go ahead and hit power here and kind of show you that. I wanted to show you on the camera that it shows me where it wants the weight. So for instance, it wants 90 grams of weight on the right side and 29 grams of weight on the left side. But the cool thing is the arrows almost line up with each other. So by putting weight on there, it's going to affect it on both sides. So I don't know what I did with my putty. So, my turn, as you can see, but on my right side, wants the weight, right? There. Which ironically lines right up with the key, because the key's missing, right? Because the balance is with the key. So I'm just going to put this on here and run it just to show you, that's how we would do it. Add weight to this spot. Not with just putty, just calibrated. And it's not turning. It's not turning very fast.
Shouldn't go anywhere, but just be on the safe side.
This is the pickup eye. So we've got reflective tape on the shaft, so it picks it up. So what it's doing is, when in reference of balance, you're doing 0 to 360 degrees. Okay, so each one, and I could count how many fins there was. Just say there's 10 fins on there. That would put each one at 36 degrees. 10 into 360 divided by 10. So I put that weight on. We'll hit OK and see what it says. Yeah, we're good. Okay, so for instance, before I put that weight on, it wanted 89 grams of weight on that one side. So I put 50 grams of weight on. Sure enough, it wants 35 more grams of weight on that spot. So anyway, what we're doing is looking at the mils up here. That's mils is also vibration. Some people refer to it as inches per second, but the mils spec on this motor is, like I said, 1.25 mils. So we would still have a long ways to go to get this thing in spec. But yeah, I just wanted to show you by putting the weight right where I did, which is right there. See, it still wants more weight there. Like I said, it was at 90. I put 50 on. It still wants 35 more grams. So anyway, if I was balancing that, I would, probably that's normally what we'll do. We'll get it as close as we can with putty, so we're not drilling a bunch of holes and making it look like Swiss cheese. Because inevitably, whenever you're balancing, it usually likes it in one spot. So we do a lot of field balancing too, and I try to only ever put one weight on when I'm field balancing. So you might run it, calibrate it. It might want weight here, so you put the weight here. Well, now it actually wants a little bit of weight here. So instead of drilling in two spots or putting two weights on, I would cheat it back towards this phase or this angle, if you would. And usually it works. So usually just, especially out in the field here, we're dual planing, right? So we balance on both sides. But in the field, I usually, it's a fan and it's a single plane on one side balance. So. But yeah, so sometimes it just depends. This one, we drilled holes through the fins and added bolts and washers. Some of the rotors have pins here where we've got these washers, right? They just kind of go on a pin and you smash it down. Just depends on if it's an impeller, like on a pump. Usually what we'll do is take material off the impeller rather than adding weight. In that situation, we'll just take it off. So yeah, just get it down, and then what that does is it prolongs the life of your bearings. And I know Matt would attest to this. His plant, a lot of their motors have vibration equipment on it. I mean, if they're very important, then you have your caliber or your alarm system set to where if this bearing starts to go, your vibration readings are starting to climb, with your equipment on there, it's preventative, right? So you see that bearing starting to go in fail mode, so you can pull that motor out and get it reconditioned rather than having it run to failure. And you could have it back in a couple of days versus at, a week to 2 weeks. Just sometimes it depends on the wind. So but balance is a big deal. I mean, we check every single rotor on every motor we do in here. So like I said, it's going to prolong the life of your bearings. A smooth motor is a happy motor. So any questions on balancing? No? Okay. Probably run back to the burnout level and show them what that's all about. Okay. Okay, so this is our burnout oven. We've got a couple different sizes here, but you can see we've loaded it up. Like I said, when a motor comes in, the winding is varnished. It's hard. So we will cut one end. You can kind of see this is a scrap one, but it's one end is cut. So then when we burn it through our 10 to 12 hour cycle, it takes all that varnish off and we're able to pull those coils out and count them. We'll make data sheets or data cards, right, prior to burning a motor, which tells us like our horsepower, our frame, our speed, our lead size, our lead length. So we know when we rewind it what to go back with. If we rewound a motor and send it back with 8-inch leads, we'd probably be getting some phone calls. So, to hook a motor up, especially a bigger horsepower, you only got that much lead. It's kind of a pain. So we take lots of notes. And we always err on the side of longer leads rather than short leads. You can push on these. Once they're burned, you push that and it's pliable. So, and then once they're burned, we'll pull each coil out, count it, and write it down on that data card. So we know how many wires in hand, what size of wires, and then the hookup, the internal hookup, as far as where your leads tie into your windings. We have to diagnose that when they come in. We'll burn the crown, and you guys might have covered this in your electrical, you might not have, but there's star or delta on your power supply. An electric motor hookup, it's the same thing. We're either star or delta.
You have a Y hookup or Y type transformer, and you have a delta type transformer. You get different results from different hookups. Yep. Same thing here. Only in ours, the only difference is now we have to maintain a certain number of circuits in that type of hookup. So it's just a step further, but it's really no harder than understanding how a transformer hooks up. So very simple if you actually just break your down into the base elements.
Any questions on the burnout cycle? Any of that? No? All right. Okay. We can run over to the winding area now. So this is one we just threw up here for example. We're going to be rewinding this, but typically what we do, once they come out of that burnout oven, we'll sandblast them, right? To make them all clean. So this isn't like this, but we didn't have time to get there on this one yet. But I wanted to show it for the class. So this is kind of the, and you can kind of see on this one that once we clean them and test them, I talked about how, and I don't know, can you zoom in right here? Okay, here's a damaged spot. So this motor blew to ground right here, right? So it had a failure in the insulation paper and the top sticks and all that, and it actually blew through and melted these teeth together. So what we're gonna have to do is go in with a die grinder or a carbide bit and grind that copper out and separate those teeth. What that's gonna do is create a hot spot if those teeth are stuck together. So I think you're only allowed 20 degrees over or variance in your core. And I can tell you right now, if we put this on the core tester, this spot would get 20 degrees in a matter of what, 10 seconds? Where's Justin?
Yeah, right.
Yeah, 10 seconds.
Yeah.
Because of they're stuck together. So, but that's, like I said, we're not there yet, but that's what we'll do. So once the core test is good, then we can go ahead and cut and install the slot liners, slot paper, which is what this is. We've got a shear over there, and our slot liner paper is on rollers. So we just measure however long we need by our width, cut them and install them. We referred to the pitch of the motor. That is this right here. So for instance, this is
1 to 10.
1 to 10. So this is 10 spots right here. So is this a 48 slaughter?
48 slot.
Okay, so there's going to be 4 coils in a group. So when we spin it up on our machine, and we're going to spin one just to kind of show you what it's like, but when that machine built it, it would build 4 of these at one time. So that would be phase A or phase 1. We would lay those 4 in, and then the next phase, the next 4 would go in, and so on and so forth, just until we get, once you get to that 10 pitch, then you start laying them down, because this will actually have a coil underneath it. So, and I'll show you what I mean by, we're going to spin another one up. So the bottom of it will be here, it's going to come over, and the top is going to lay on this spot right here. So we've got a center stick to keep those separated so they don't touch. So yeah, you want to hit spin that real quick? Yeah. So like I said, we'll go in and enter however many coils we have in a group, and then we've got different wire sizes. We have everything here from a size 23,
Yeah, well, I mean, we
22, 23, which is pretty small,
we got it from a size 30 something.
up to size 14. The bigger the number, the smaller the wire. So, but anyway, what we'll do is when we pull that coil and count it, we know however many wires in hand it has, right? For instance, we just spun this up for the class, but this has 4 wires in hand at 6 turns. So there's 24 wires in that coil. So now we're going to spin up another one and lay it in. So each slot will have 48 wires in it, a top and a bottom. So
And each slot for these is actually measured in circular mills for
Yep.
slot mill.
it's true.
So
You guys have you talked about circular mills a little bit?
it's a lot like your wire shop.
Yep.
500 pieces. The same thing. We're not kind of an industry standard. We're not really supposed to go below 150 kc per amp.
Yep.
All right, ready to spin?
Yeah. So yeah, we would go through and tell the machine what we're doing. So for instance, this is a 48 slaughter, so we would be building, with that head, we could probably build 2 or 3 groups, 3 groups at once. So we're not going to do that here, but so we would enter all of that in the computer and then close the lid.
Basically, this is the sample stage. It's
Yeah.
Yeah, we're trying to basically
Get your size. Yep.
size and slot.
Because you can't just go building a big long coil in there. The longer the coil, the easier the motor is to wind, but a lot of times you don't have room, right? Sometimes there's an internal fan on the rotor, sometimes your end brackets are flush, so you have to take that's part of your data taking is realizing your extension, your coil extension, so you don't just sometimes it's not very comfortable to wind, but you don't have a lot of room, so you gotta keep that coil size down. So
All right. Then just hit the go button here.
So if that was a group of 4, it would have gone to the next slot, spun up 6 times, gone to the next slot, spun up 6 times. Like I say, round and wound coils we build here in house. The form coils we order. you have coil trees over there. It'd be nice to be winding this one so you could actually see, but if it made all 4 coils, they would be connected, right? So you're only laying one at a time, so you would have a winding tree right here holding the rest of your coils in that groove. So, like I said, this isn't exactly set up for this one, but we have slider paper on this side. It helps kind of guide that wire in your slot, right? So you can kind of get it in there and just push it through, and that slider paper actually protects it from getting scuffed. So now, just take a couple wires at a time and go down.
T-bar.
No, shouldn't.
So one thing a lot of people really don't quite understand when you talk to them about rewinds is just how labor intensive they are. A lot of people think that we just stand back and throw these coils in and have them done in half a day. Basically, he's doing that at about 3 wires at a time. Yeah, that's it.
Like I said, this isn't even the correct wire that goes in this stator, but I just wanted to do it to kind of give you an idea of. Yep, you just line them out, put them in there, and then shove your top stick in. Yes, sir.
You've got paper separating this and that. So
this stuff right here, the slot liner?
Yeah, this slot liner.
Yeah.
This paper actually on the top.
Yep.
So these are all going to be the same phase, right?
Inherently, the ones here, if we were winding this, the one right next to it would be the same phase in, let's say, a group of 4, which this would be.
But to keep these stresses, right? So that's why we lay the center stick.
Now, and technically,
to keep the stresses at a minimum.
In your pitch here, you can have 2 different phases in that slot because of your pitch. Because it's a group of 4, this is a 1 to 10 pitch.
So I have to draw it out.
You're out of the math.
But
so you're gonna have. That's what that's supposed to do. It's supposed to help divide the phases. And the other thing is when we actually do the groups, we'll divide the groups by phase cloth.
Yep.
To prevent arcing or straight up.
Yeah. So we'll lay that group in. This is phase cloth right here. Right. So then you would lay it. Once you laid that group in, you would lay your phase cloth in, just like that. Okay. So then your whole group lays right on that. So that's separating it from the next phase that goes down. So, yep. Some guys use this on when I hook motors up. Right? They like to use that on the leads.
It's kind of
Cambric. Yeah, that's the word I was looking for. So, anyway, yeah, just tell the machine what we need it to do, how many groups, and then build them up from there.
Now we're spoiled. We have the automated machine right now. A lot of machines out there are still. It's an electric motor turning the head, but
you're the tension, right?
Yeah.
You saw Justin close the hood and just hit go because it's ran through a tensioning system. The shop I used to work at, we were the tensioning system. So.
And you had to count the number of turns individually. So we're really lucky with the equipment we have here.
Slot line
yeah. Yeah, I can't remember the thou. I know on like our center sticks, they're 20 thou thick. Top sticks are 24 thou thick. I want to say our paper is 12 thou. 15 thou. Okay. So there is different size paper. 98% of what we do is our thicker paper. Sometimes on the armatures, we've had to use the thinner paper because they're so tight. Like I said, with armatures, you're containing everything on the rotating part or the rotor, and this is the stator. So here you have to keep your clearance down, away from the bore. With an armature, you have to keep everything inside the diameter for the clearance, if that makes sense.
Gabe,
Yes.
how long does it take you to coil a?
That one will probably be wound in with coil insulation. We could do that one in a day, or making the coils, and actually from this point to test the core and get the wire in it, we could do it in a day. Might not be hooked up till the next day, but we would have the coils in it in a day.
The hookup on this would probably take about half a day.
Yeah. And the hookup is where all of these, right, your ends have to tie together. That's the hookup. So just imagine if there was a set of 4 coils here, you would have one start and one finish, right? A start and finish. So that might go to a lead, it might go to a jumper. It just depends on how we diagnose it when we burn it. That tells us the hookup.
Now, is this like one of the tedious tasks of engine build, electrical engine?
I actually like winding.
Really?
A lot of people think it might be tedious, but I mean, it's a little frustrating to learn because you're like, why don't you just go in the slot wire, you know? But there's manipulations and you learn how to feather it, right? Like it's called feathering the wire. You know, you just get them to lay nice where they're comfortable and then just lay them in there. So, yeah, just baby steps. So, and being patient, I'll be honest, once I became a winder, I became a lot more patient because you realize it's not about fast when you're winding a motor. It's all about doing it right and doing it right one time. Because you don't want to go fast, and that's a lot of money and time to envelop in something to just have, if you went fast to, you know, you missed some wires and they went behind the paper and, you know, now you're testing it and it's grounded and you're not sure where, so now you got to try and find it.
So is it all senior guys work in the shop, or do you have new guys that do this and you'll walk over and going, nope, you're gonna have to do that all over again?
No, we've got a couple new guys here in the winding department. Yep. And they both kind of had winding experience, not necessarily motors, but they had wound transformers. So,
The thing about winding electric motors is you don't know you screwed up until you think you're done.
that's right. No, that's true. You won't know until you go to test it if you messed up. So that's part of why I say being patient, you know, because you don't want to get to the point of testing it and have it fail, and you know, especially if you spent 2-3 days winding it.
Right.
No, it's actually
It depends. It depends. Matt would know a lot more on that, but
So yeah.
the question is what, efficiently, at what point is it you just buy a new one versus?
So typically, it's kind of balancing that. What we have to look at is what we have for spares. So if I lose a motor and I put the spare in, then I go and say, okay, what's the cost to rebuild? What's the lead time on the new motor? Well, if you know anything about electrical stuff right now, lead times are insane. I'm looking at putting in a transformer and it's 20-25 minutes. So I look at that and then I kind of base it off of like 60%, 70% of my motor. If I'm worried, because like I said, I own these motors, so depending on where it come out of, if I'm worried that they're going to burn it up, I usually send it out, even though I may pay more versus the cost of the money. But at the same time, I also
It's just like the heat. Yeah.
Well, and that brings it good scenario too. The motors we send out of here are actually better than they were coming out of the factory.
Higher insulation value.
Yeah, higher insulation value, better connection. A lot of the factories that produce them, you know, Gabe's seen them where they just heat up the connection and they put a little dab of solder on it.
Little tiny dab of solder and call it good.
And that's it. And where we actually do a full weld of everything.
Encapsulate everything and then insulate.
And so it's just, and then afterwards, you know, our tolerances here for like machining and everything else and balancing is a lot higher than, again, coming from the factory. And so it might cost a little more Now, if you go into, let's say, single phases, definitely cheaper to buy, to answer your question directly. Just because we can't wind a single phase for what they're selling.
Yeah, no way. Even a small 3-phase for that matter, right? Unless it's OEM, we talked about that earlier, original equipment manufacturer. But so for instance, this is a 50 horsepower. We probably normally would not wind a 50 horse T-frame, but this is a tunnel fan, right? It's a special application. Is it dual shaft?
This is a dual shaft.
So it's got fans on both sides, made for ventilation in the underground mines in some of the gold mines in Nevada. But that's what these tunnel fans for. So they're a special breed, right? We don't just have a 50 horse double shafted motor to go put in this place. So that's why we're rewinding this one, because it's particular, it's special. Because normally a 50 horse is probably not worth rewinding.
Unless there's no machine.
Even 100 horse, even 100 horse is. I've been to classes and there was motor shops that like we don't even look at anything under 100, right? So
Yeah, so that bar is changing.
Yeah.
So that's like a big part of my job is looking at, okay, what's the cost efficient to rewind versus purchasing. So 3 years ago, we were throwing away 100 horse. Today, we're rewinding 50 versus 60. So, like I said, my bar is constantly changing, constantly evolving. That's why we get calls. That's why.
yeah.
Send it like a scrapyard, and does the scrapyard just say, hey, we're not going to get anyone here, but we'll get a little bit back, so so
You'll
we're
get
set,
one if you separate them.
yeah, we're set up a little bit different.
Yeah.
We're gonna that deal through what's our name?
Salvage. Yeah.
Salvage area. But if you had a motor first, you want to take your time to take it out the couple, and get rid of the company. So you
Other than that, they only get if they're together, they only give you standard scrap price. They won't give you price for the copper unless you extract it. Oh yeah, no, it's not easy.
yeah,
I mean that's why we have burnout ovens, because you ain't getting it out unless you burn it off.
and that's what those guys do. Is they send it to a bar,
Yep.
separate it out, and resell it to somebody.
Yep.
So right
That's
now,
what we do. But we
Yeah.
sell all of our copper to places all over. We do it.
so right now the only installation is paper. But ideally, after this was completed, and you've got your paper plus your what would you call it?
The top sticks and center.
The
Oh, face cloth.
and
Yeah.
stuff. After all of that is done, then you apply the varnish at like the very end.
That's right. And like here, we've got glass tape and sleeving, right? That stuff right there. That helps. That's what we insulate our connection with, right? So we'll solder them together, glass tape, and then put sleeving over the top of the tape.
So at the end of the day, a motor has like 4 or 5 different layers of insulation
Yes.
inside of it.
Yep. And each wire is coated. I want to say the like 20 dips or something is 20 times this has been ran through, right? If I was to take a knife and scrape that off, I could scrape that coating off and get down to just copper. But this is all VFD rated wire, inverter duty wire, so it's got more layers of varnish on each wire.
You mentioned that sometimes you might put a whole thing together and then you'll find out you have a short inside somewhere. Would that theoretically just happen like if you put it in badly and you scraped off the varnish as well? Because you think the varnish wouldn't necessarily...
You're right. That could happen. Knock on wood, I've never had one test bad after I wound it, right? That goes along with being patient and using stuff like these sliders to help protect all that. But to hook it up wrong, I have done that, right? We've got, each motor might have a different connection, right, on this end. And yeah, I've hooked them up wrong. Luckily, we have test equipment, but I caught it before it was varnished, so I was able to fix it, because once it's varnished, that's not very easy to pull up. So,
is there a situation where like maybe everything tested fine because you've got the coating on the wire, but in reality you accidentally put a wire behind the paper Is that going to make it?
It would show on that test. That would be a ground issue. Okay.
Even though there's varnish, your test will just punch straight through the varnish and tell you, hey.
It can, absolutely. If I lay one of these, one wire behind that paper, it'll tell me.
Okay.
It'll usually, so for instance, 480 volt winding, okay, we will test that at 2.5 times plus 1,000, the rated voltage. Okay, so 480 times 2 is what, 900 plus 1,000, pretty close. So that should pass a test at 1900 volts.
But if it was just sitting on there, the varnish would come out.
No. So,
That study goes back to the megger. The megger doesn't stress it. It's not going to stress it.
that's right. Because
Search.
if my copper wire was behind that paper, it would pass a 480 volt test. It'd pass a 500 probably. It's not till about 900 that you start to see your needle drop. It's like, well, something's right, because all that insulation should very easily take that voltage, that amount of voltage on a test. So if it starts to drop, then you have a ground or a spot where you have wire touching your frame.
And
Yep.
again, like we were talking about the megger, looking at that voltage, if you've got moisture in there, that can also, you'll start to see that bleed. And so if you're not getting the solid voltage, you know, okay, you got this.
Yep. So, but that's the cool thing about our test, right? It'll tell us that before we varnish it. So, yeah, if we do our due diligence like we're supposed to, we should never have to pull one up after it's VPI'd, you know, because all that needs to be tested prior to ever getting varnished. And that's what we'll do, a high pot or a meg test, a surge test, and an open stator, which is, we induce a low voltage to this. For instance, probably about 60 or 120 on the voltage is going to give us nameplate amps, pretty close on a 480 volt motor. So if that's, you know, rated at 50 amps, then once we wind it, we can induce a low voltage to it and test it on all 3 legs and make sure we're even. So
Yeah, so typically when I send a motor to these guys, I can tell on the track. So when I get a motor in that's been rewound and new, we take a baseline test. So that tells us all the resistance, all the inductance, everything. And then every quarter we test it again. So I test them with 2 different, one's a static, one's a dynamic. So dynamic is what the motor is doing when it's running. Static is what it's doing stationary. So when I send a motor to these guys, I'll tell them this thing's managed. Turn short. So bearings. I've been pretty accurate.
yep, very accurate. So
And that's our goal, is we want to get it here reconditioned.
prior
There
to
are times that I call them up and say, guys, I got a 400 horse motor, you need to turn it in. And they can do it in 36 hours.
Yep.
They quality English.
Yep.
They get that motor back, it's gonna be. But I like these guys.
pushing all the time. And we appreciate them not being pushed all the time. It's okay once in a while for it to be a couple weeks before you get it back.
So I'd like to send them. You only have to do that.
So we can actually install one of these for you. Get on that side. Yeah, maybe. I don't know.
Who's getting sweaty over here?
No, it is not. So
I'm gonna grab the iPhone.
yeah. So there again, this is just extra insulation value of felt blocking. What we're doing is we're installing them right here so these coils don't rub together, right? Because every time this motor starts and stops, these coils will flex. Can't necessarily see it with the naked eye, but they will, right? And a lot of starting and stopping and flexing.
Yeah, I got a video that shows GE put one out years ago, showing us the
Flexing. Yeah, I've seen them in classes. I've seen it. So there again, this coil is, like I said, pre-measured, pre-made, so they come to us already made like that. So it is imperative for us as a shop, and we get at least 2 sets, if not 6 sets of eyeballs on everybody's measurements, because you don't want to order a $12,000 set of coils and have to be wrong via your bad dimensions taken, right? So you didn't take good measurements and it cost you. Yep. Okay. Yep. Go ahead.
Start your side.
Yep.
It's over there on the other thing.
Ah, yep. Tap it down here. So we're just seating that coil down in the slot.
And so that, up here. Okay.
Micarta blocks, rubber hammers. That's important because you don't want to hit it with a steel hammer. So, yep.
There you go.
And we'll seat that.
Top stick.
Take the top stick.
Top stick. Is that one the end? Slides in there. It doesn't just grab everything and drag it.
That's another thing. The form coil has a notch right there for this. This is a different type of top stick rattler. We passed that one around. This one is kind of contains the wire in the slot. And this top stick actually holds everything down. So it's actually got a groove in the laminations for the top sticks. Okay, that's tied, and then we've got the ring. Tied. That's what this fiberglass rope is here. That helps protect. I was talking about earlier, lots of flexing, right? So that's what this rope does, is contain all that. But the further away you come from your slot, the more flex you're going to have on your coil. So that's pretty far out. It's like 7.5 inches out. So a lot of flex. So we install those surge ropes, and once they're varnished, you know, that becomes like concrete. Yeah. Just put it and tie each one.
Instead of shirt rope, and once we get BPI pulled into this, that one is on here.
And then that tie just helps contain that rope, and once it's all varnished, it's there for good. So. Any questions on winding? No? How much longer we got left? When do you go to 9?
Yeah, we can break it.
Almost that now.
That's,
But,
Gabe, what's going to happen? You're going to break, and then they're going to finally ask you questions.
well, that's good. Yeah. They need to ask them if they have some. So. What's that? Yeah, we can't really get over there. I guess I can kind of go open it, but we've got too much stuff in there.
So, right now, we don't have to show you. Maybe you just explain.
Yeah, I can talk about it. Matt just brought up a
Why don't
good.
you stand over,
stand over here?
Yep, that way we can get a better shot.
Matt just brought it up. I kind of explained it a little bit about the VPI, the vacuum pressure impregnation. I kind of did go over that. Talked about how, you know, we'll pull the vacuum on it, get all the air out, and then induce the product and then apply 90 PSI. And like I said, this motor will be, we'll take all day to do that motor. It'll take 8 hours to VPI motor. You need to be at least 2 hours per cycle. There's 3 cycles. So on a form coil, you should be at least 6 hours, but we'll go all day. We'll go at least 8. So we could cut one open, but each one of these coils has, I don't know, 20 wraps of mica insulation, at least. I can count them, but so what you're doing with that VPI, by giving it that amount of time, you're allowing the varnish to completely penetrate all the way through your insulation into your copper wire. On a random wound motor, 45 minutes per cycle and you're good. But with the form coil, where it's got that much more insulation on the coils themselves, we do a longer time to allow the VPI varnish to get all the way down to the copper wire.
So not all shops have a VPI.
No.
They usually just have a dip tank and also they drop it in. Maybe
yeah, like I said, we have both. The other varnish, like I said, we use on a dip and bake. Only on all of our new rewinds do we VPI, and it should only ever have to be VPI'd one time. That's how, because if it does its job by sealing everything, then you really can't get any more varnish penetrated because of the vacuum / pressure impregnation process. So once they've been VPI'd, that is the best way to go about it. I know it was an expensive setup, and they bought it before I got here, but it's worth its weight, that's for sure. I haven't seen anything break down due to breakdown in insulation on a VPI. The old varnish, I think it cracks, gets brittle, I think a little bit more easier than the VPI varnish. It just withstands that heat and the stresses a lot better than the normal varnish. Or the older varnish, I guess, I don't know the numbers on it, but yeah.
Yeah, so like when we do the early detection, when we bring a motor in prior to failure, we'll do like a steam clean, new bearings, maybe some machining on the bearing housing, and sometimes a dip and bake. Kind of depends on the condition of the insulation. That adds the extra layer on top of the VPI that's already happening. Most of our motors, a large majority of our motors are already VPI.
Yep, if they've been rewound. Yep. So, but at least on the recondition, even if a motor comes in wet, doesn't necessarily mean it's grounded due to burnout. Just the moisture, that's what the bake oven will do. So if we don't physically see a blowhole and we don't see any carbon or anything where it might have blown up, rotor didn't drag any of that, we physically don't see a hole, then we will always, because it always could be moisture. Even if we don't see it with the naked eye, it still could be moisture related. So if we don't see an actual burn, we'll steam clean it, bake it dry in our bake oven for a minimum of 4 hours. On a smaller one, that one would probably be 6 hours at 315 degrees, and so that would get any residual moisture out, and then we can test it. So winding, here's a good point. A winding is either a pass or fail. It's not like I've heard over the years guys say, oh, my windings are starting to get weak, it's tripping out. Well, it's not due to the winding, because the winding is either a pass or fail. So that's one thing to keep in mind as you're testing these things over the years. So
you will be asked that question. Can your motor be getting weak?
No.
Pass or fail.
Yep, it's a pass or fail. Could you have a bearing going into failure mode, causing over-amping, causing your motor to trip out? Absolutely, but that does not mean your windings are getting weak. What that is a draw causing overcurrent, which is going to cause an overload or trip situation on your control side if everything's hooked up right. So a lot of guys bypass their protection, and so that motor just keeps running, and it finally blows, and it takes everything back all the way to the hole. So I'm not the electrician side. I don't have that side of it. But what I do know is how important electricians are for what I do, right? I mean, it's a communication between them and us as a motor shop, to put out the right product, to do a timely job as quick as possible, you know, in a timely fashion and putting out a good product. And at least by you guys going through the electrical program, at least now maybe by doing this class, you'll kind of understand what it entails, what the key parts are to an electric motor. You know, that would be the biggest thing I think that I hope you guys get out of it, because it's not like you're all going to be working on motors, you know, but at least if you're familiarized with them, I think it might help understand what you're testing when you're out there, and what can fail, and you know what to look for. So hopefully you guys get that out of the class. So, and it's a great industry, both of them, right? I mean, an electrician or a motor guy. As far as the motor goes, pretty safe. 65% of the world's power is consumed in motors. So, you know, and you know, they don't fix themselves. It takes human hands to fix them and make them right. So, but maybe, you know, if you guys just learned a little bit about what you're dealing with an electric motor, and you can put it to use someday, then I would say the class is a success in that aspect. So that's how I feel.
Justin, as an electrician?
Kind of a loaded question. As an electrician, I think it's nice to learn what we've been going through tonight, because it's like I've told people in the past, when I went through the program, the difference between an AC and a DC motor was an AC motor had slip rings. I mean, that's
just not even,
that's not even
entirely true at all.
Yeah, that's just touching the tip of the iceberg. And when I started here, it was a complete game changer. I had no clue really what I was looking at. You know, it's built up a lot of confidence for me as an electrician to be able to go out in the field and listen to, let's even go into a single phase. Listen to a single phase fail to start and say, oh yeah, you got a governor stuck or a switch is stuck or something, you know. And it's all in all, it makes you more valuable, and it makes you feel better about yourself, more confident in the industry. You know for a fact that whatever they throw at you, you're going to be able to sit back and troubleshoot it. On the motor side, it's kind of the same thing. You see a lot of the same thing every day, but then you get that one thing that no one's ever seen before, and makes you scratch your head and wonder how that happened. But it makes you more valuable in the long run, being able to do what you guys are going to be doing. And so,
right?
Yeah.
I mean, there's a lot of work out there in the electrical end, but you're not necessarily stringing wire all the time.
No. I mean, a lot of people, they have the misconception that electricians, all they do is play with wires, run conduit. And, you know, I can't tell you how many days I've spent on the back of a shovel more than anything else, you know. And, then you get on the other side of it all, and, you know, they think that we basically rub two sticks together and it happens. And then when they find out that to figure out that rolling offset, you had to use trigonometry. And they're like, well, I can't even pronounce trigonometry, and you're doing it. So, you know, it just, I think we have a common misconception. There's a common misconception out there that the labor side is unskilled, when in all actuality, it's one of the most skilled fields out there. And so, you guys should be proud when you guys do get out in the field and doing what you're doing, to know what you know. Because tell you what, not many people can actually look at this and understand it. So,
And you're problem solving.
Yeah.
You know, that's what you do.
nobody knows, and that's the thing, nobody knows everything. I mean, we could be in this field for 20, 30, 40 years, and we'll see something new every other day. And the minute you think that you know it all, you don't. So just be willing to learn, be open.
Right. All right. Matt, thank you very much for putting this together, Matt. Really appreciate it.
Absolutely. And these guys, Keith couldn't be here. He had prior engagements. But
It's Keith's shop.
it's Keith's shop. So Keith's a great guy. All these guys are awesome. Like I said, when I told them what we were gonna do at Simplot, they welcomed us in, and like I say, when a motor comes up here, I'm right behind them in a truck, and they're cracking it open for me, so that not only do they learn, but we learn, and we have conversations. These guys had a motor up there from our Smoky mine. Unfortunately, we didn't get to do the test that we wanted, but Justin hadn't done that test. My technician had, but we're going to get him down to the plant. We talked with Keith and get him through some dynamic testing. But, you build those relationships over your career. And me and Justin actually worked together when he was an apprentice. I don't remember which job it was on, but he still likes me, so it must not have been too bad. But you start building these relationships all around, and we rely on these guys. So when I do make that phone call, hey, I need this motor turned around as fast as you can, they drop what they're doing because those can wait, and mine moves to the front. So like I say, one of the big reasons I like to bring you guys into this type of shop is to show you the versatility of being an electrician.
Which I applaud Matt for that, as I don't know if any other program was doing something like this. It was pretty cool for him. When he first approached me about it, I thought, well, heck yeah. Because I heard Justin say for years that there's like 3-4 pages in the book about motors. There's just not a whole lot, when you're going through your apprenticeship. So,
well, and you go through it fast,
yeah.
and you have these pictures, whatever. They don't tell you anything. I mean, yeah. When I went to Lamb Weston, and it was a great introductory. I mean, you just change motors because that's how they run them. And then when I came to Simplot, I was like, man, there's got to be a better way. Because I hate it, fighting with the mechanic. No, it's this, no, it's this, no, it's this. Well, now I have the technology. I'm like, no, it's this.
To help identify if it is indeed the motor, if it is indeed the supplies, the feeders or the bucket, whatever you want to call it.
Well, and we can track it down to even an operator or a change in process or something like this. I can go to our production and say, something's changing in your process because our amps are starting to creep. That pump's brand new, and I know that motor's good because I got this report. So then they can start looking at things and go, oh yeah, you're right. We need to go into a cleaning cycle. And it creates longevity in all of the process. Your piping, your pumps, your bearings, everything. Because the less you work those things, the longer they're going to last. It's kind of like us. The less you work me, the longer I'm going to last. So, other than that, I appreciate this is probably the biggest group we've had actually show up at the shop. It's awesome.
So thanks everyone for coming. I really appreciate you participating in this field trip. Matt's going to have one at Simplot. Now that one, we can't bring our cameras in. So please, everyone, if you can attend the Simplot one, that would be great. Show some support for Matt. He would appreciate it. It makes him look like a big guy at work. Again, I want to thank you all for coming. And I'm sure as soon as I end the session, you guys are going to have real questions for these guys. And thank you so much.
Appreciate it.
Thank you.